We were, prior to my coming up the elevator and being scared for my life, which happens to me anytime I'm around crazy heights, we were at a restaurant like a mile south of here, and this is really cool for us. We've been working on this for a while because some of you have already seen a variant of the demo that I'm going to give. But for the first time, we actually ran our live demo on our testnet, and that's very, very exciting for us. And that's the first time I've ever said those words to anybody above a quiet whisper, right there. So I'd like to impress upon you that one of the contributions that we make at NuCypher, I really don't think I'll need the microphone. Is anybody having trouble hearing me? I'll blast to the back. We'll be good. We work a lot in the realm of cryptography. We've rolled some of our own crypto, that hot lava stuff. And we've demoed it for you at, some 20 events over the course of the past year, thereabouts. But another area where we work is an area that I, correctly or incorrectly, typically call cryptology. And this is the experience by which our higher order cryptographic objects learn about each other and relate to each other through a coherent narrative. Now, usually the cryptology of our culture involves two imaginary folks, Alice and Bob. And we take for granted that Alice and Bob have some existing relationship, and Alice has this pressing need to say something to Bob or to transmit a message in such a way that Bob can verify it has come from Alice. We have encrypting and signing, right? We have tried to add slightly to the shared understanding of cryptology by adding additional actions and additional characters to the cryptological narrative. And you might say, oh, there are already 20-something characters that are widely recognized as part of the cryptological narrative. Them Sybil, right? This is the one that tries to gather a small majority of powerful actors in order to manipulate the network that isn't Byzantine fault tolerant. And Eve, who tries to eavesdrop. And that's true, but those characters are usually used to describe some kind of process that lives outside the cryptological narrative. What we've done is built more characters that live directly inside the cryptological narrative. The first one of those, and the one that kind of makes our network special, the thing that we think people will pay for when, the thing that we think the blockchain makes worthwhile and that people will commit on-chain transactions using cryptocurrencies for, we call this character Ursula. And Ursula takes a message that was encrypted with a key that Alice made, and instead takes that ciphertext and re-encrypts it in such a way that Bob can read it. So instead of Alice encrypting directly with Bob's key, Alice is able to make a key so that anybody can encrypt with that key, and Ursula can re-encrypt it so that Bob can read it. In fact, any number of Bobs can read it, and Alice decides who's in and out of the club. We call that a policy. Alice can disappear from the network entirely, and people can still re-encrypt for Bob. And Alice can subsequently revoke access so that when people continue to encrypt for the same key, Bob will no longer be among those for whom it is re-encrypted. So this is a slightly different take on the cryptological narrative that allows some different scenarios. One of the use cases we sometimes talk about in a quick elevator pitch is the idea of a Dr. Bob, where Alice has a number of medical devices, and she wants those medical devices to be able to talk to her medical providers, and she's able to grant access to those medical devices, from those medical devices to her medical providers without anyone knowing who anyone is. And then subsequently, if she stops liking a medical provider, she can revoke access. In the decentralized world, you might think of some use cases that where you normally wish you could reach for something like Amazon KMS. Not that anyone ever really is itching to reach for Amazon KMS, of course, but where you might reach for a coherent key management system. And again, not that I'd even put Amazon KMS in that category. You want to handle keys, and you want to do it in a way that you don't need a central authority. We think that NuCypher can be used pretty nicely for this. But again, what I want to impress upon you now is just to open your mind to the idea that Alice and Bob, in a decentralized world, Alice and Bob aren't the only meaningful cryptographic actors. Is the demo going to crash? I really don't know. I honestly don't know. All right, just a little bit of singing and then we'll try it. Oh, I saw other people with instruments here too. If anybody wants to hop up with an instrument and you feel like it's your zone, feel really free to do that. Sufficiently blessed now that it won't. The blockchain projects that you see that people do quick code read-throughs are written in what? JavaScript and Solidity, right? Now we use Solidity, of course, because we have smart contracts, but the logic of our code is all in Python. I think that's kind of cool. I think Python provides a nice syntax and semantics and, most important, culture for describing the cryptological narrative that I've been talking about. We try to bring characters together and have them interact almost like a screen. So let me read some of this. Let me read what's going to run here for you. Okay, line 65 here, we have Ursula's seed node. I described Ursula. In this case, you have to know some Ursula in the world. And so we've hard-coded one that we have running on, well, on AWS. And such is life, right? Okay, but this can be a node that you run if you decide to stake NuCypher tokens. This can be a node that you trust if for whatever reason you have a pre-existing trust relationship with a node in the swarm. It can also simply be a node that you choose because it's staking a lot of the token. So there are, in the logic, while we will provide sane defaults in our network, you can learn via any beginning node you like. Okay, now here we have Alice. Okay, we talked about Alice already, and notice in our code we tell you, here's Alice. We have a class called Alice. I had it up there while I was playing a little bit. And this class defines the powers that Alice has, and the capabilities and her role in the narrative. This is, look, we've got commented out lines. It's like, we really were just working on this at a restaurant. I'm not even kidding about that part. It really just happened. So Alice learns about the seed node. In this case, I have her learning on the same thread as the one that's running. That's not super important. Here, this is federated only. This is going to be a federated only demo. And she has to save TLS certificates for other nodes. Nothing terribly exciting going on there yet. Okay, but here we have our policy details. We have a time when this policy is designed to end. We have values for M and N, which is kind of like a Shamir secret sharing scheme. I'm going to turn these down a little so it runs a little bit faster for you. And we have a label. Now here I've kind of emulated a path with the label, right? So I'm, again, kind of reaching toward the idea that this might be used in some cases the way you might use a KMS, while you have a key for each path, right? Alice, now we've got Bob here, right? So Bob, again, this is not important anymore. Bob is going to use the same seed nodes, doesn't have to, could be a totally different seed node. Same federated only, all the same details. I'm only making one Bob here, but again, we can make any number of Bobs to be included in the same, that Alice can delegate to for the same label. Okay, Alice is going to start her, what we call the learning loop. We've kind of also rolled a protocol for nodes learning about each other, which may be the subject of another demonstration someday. And then here's how we get our policy. Alice grants. Say again?
The learning loop, what is this? Like internal process loop?
Yeah. So yeah, we initially used Kademlia, which is one of the popular protocols implemented by libp2p And then we realized that we're in a situation, which probably a lot of you are, where the number of nodes that you have is never going to exceed something like 2,000 or 10,000 or somewhere in that vicinity. And so we wanted a more, what I've come to call a more intraplanetary protocol, right, where we expect everybody to know about everybody else in the default situation until things get shuffled a little bit. But we didn't need, you know, what libp2p and specifically Kademlia do with Hamming distance to, you know, have the entire network know about the nodes, even though no single node does. So it's actually very cool, and I'd love to publish it as a protocol. Maybe we call it like the intraplanetary learning protocol or the this world protocol. But for the purposes of this demo, it's not super important. But if it's something you're curious about, I'd love to talk about it and kind of show it off later. It uses Twisted, which for my money is one of the best open source projects in the world for its network engine. But yeah, so the learning loop is just how Alice, you know, Alice needs to find 3 Ursulas, and of those, any 2 will be needed for Bob to gain access. Right, so to find the 3 Ursulas, she starts with only 1 seed node, and then she's going to learn about the others through the network. What's now line 97, Alice grants to Bob, right? This is the kind of syntax that's pretty typical of our code base, right? We have one actor granting to another actor. We have Alice can verify from Bob. This is another method we have, alice.verify from, and then it takes another character. Alice grants to Bob with the label that we already set, values of M and N, 2 and 3 as I showed above, with the policy end date time. And now I briefly skimmed over it, but I'll go back just to make it very clear. What this means, these values of 2 and 3 mean that Alice will split a re-encryption key into what we call K-frags, key fragments, and she will give 3 key fragments, and she will give 1 key frag to each of 3 Ursulas. Then Bob needs to find any 2 Ursulas in order to complete his journey, in order for him to gain access to the underlying message. Okay, so it's kind of like a Shamir secret sharing scheme. You know, it's in order to decrease the likelihood of collusion. We don't know the best values for M and N yet, nor do we even know whether there will emerge such a thing as best values generally for M and N. But it is important to know that in that collusion scenario, in other words, when M Ursulas come together, the power that they gain is only to re-encrypt for Bob. They're not able to gain access to the original plain text for a given ciphertext. For that, they would need Bob to participate also. So just to be really clear, the collusion surface is Bob plus M Ursulas, right? That's who is needed to compromise the key pair that Alice has made for delegating. Tux wants to add a proviso.
Oh, I wanted to ask you a question, actually.
Oh, he's going to add, look at this. We were just working together 25 minutes ago to get Testnet up.
I was just going to suggest how that you explain the difference between Shamir secret sharing and proxy re-encryption.
I don't know, man. I don't think that's quite in the scope of,
okay.
Maybe at the end. How's that?
Sure.
Tux, hold questions to the end. And we'll... In super broad strokes, Shamir secret sharing is a conceptual idea that you can have some large number of holders of a secret, often this is called N, and a smaller number which represents the threshold, and any threshold, any M among those N are able to recombine the underlying secret. That's the broad strokes of Shamir secret sharing. Now look what happens so what happened here? We granted with Alice. Alice now saved what we call her stamp, which can be casted to bytes. This is a representation of her public signing key. She saves this somewhere for Bob to find later, and then Alice disappears from the internet. Okay, so here is where our cryptology starts to deviate from that, which you might have seen before, because Alice is going to disappear from the network, and yet others are still going to be able to share for the policy with all the Bobs being able to re-encrypt. Right? You couldn't do that, for example, with the Amazon KMS. The same person who grants access, who was there with the symmetric key, needs to be there, needs to be online in order to share with Bob. The delegator and the encryptor have to be the same person in most cases. And this is optional, as we say on this comment here. She might wish to remain online and create new policies, but she doesn't have to stay online. She's happy with the way this policy is. She's added and subtracted Bob's, and now she's got the ideal policy. Now she can disappear if she wants. Some time passes. You know how we make time pass, right? Our generation grew up with the ocarina of time, so we do. And now Bob finds himself awakening in the temple of time to join the policy here on line 119. Bob needs the label to join the policy, and he needs Alice's signing key, the bytes of Alice's signing key. Okay, so he has those two. In this scenario, presumably Alice and Bob have had some pre-existing relationship where that information has been shared. I don't know if it's... Oh, this is no longer relevant here. Get rid of these comments. See, one of the really great things about live demos is that you're forced to prune your comments live in front of them. All right, now that Bob has joined the policy, we show how data sources can share data with the members of this policy and how Bob retrieves it. We say data source here. Sometimes the data source feels like a full-fledged character, and sometimes we call it Enrico. Don't be surprised if in a future version of the code base you see it under characters as Enrico. Now, the text that we're going to share, first of all, let me skip this part. This is just some metrics that we save so that we know how fast the single process of re-encryption is. But of course, this is all open source. Feel free to look at it later, of course. So Alice has set a policy. Here's where we are. Bob has joined the policy. We're ready to make some data sources and encrypt for Bob. And it may also, at this point, if you're reading this, be helpful to imagine you have multiple Bobs, multiple labels, both. So first we're going to make a data source for the policy. Okay, here's our data source that uses this policy public key. Again, this is not Alice's signing key. It's not her encrypting key. It's not one of the keys that you're used to seeing. This is a different type of key. It's cryptographically the same type of material, but cryptologically a little bit different. It's used for a different part of the narrative. It's used for delegating, not for encrypting or signing. And here's how we generate what we call a message kit. Okay, a message kit, think of a key that's encapsulated, okay, encrypted, and a message that can be decrypted with that key. We call those two shipped together a message kit. And we get a signature here, which we can pass via a side channel or post somewhere as testimony to verify if this needs to be a publicly verified event. Okay, in this case, the plain text is a single passage from James Joyce's Finnegan's Wake, which is, kind of a strange book if you've never read it. There's very little of it that makes any sense to the plain reading, but people do years and decades of thinking about it. And so we think it's important to disclaim that the matter of whether the encryption makes the passage more or less readable is left to the reader to determine. Okay, so we encapsulate a single message. That's the plain text. Again, a single line from Finnegan's Wake, not the entire book. And now the data source wants to be verified by Bob, so it has to leave its public key somewhere, right? If your Dr. Bob wants to verify that in fact this data did come from the medical device that he was expecting based on his previous relationship with Alice. Now it can save the message kit somewhere. IPFS I think is a great idea, but wherever is fine. And then it can also disappear, although maybe that same message kit might want to continue transmitting more messages as those become appropriate. But here we just want to show that the data source can be deleted. Now we come back to Bob. Okay, Bob reconstructs the data source from its public keys, data source from public keys, and those are the public keys that are needed along with the label that he's trying to use. Now we can retrieve the original message. Here's Alice's public key, which he has dusted off. Remember that was saved for posterity. And now he has the delivered ciphertexts. Bob retrieves the message kit. Okay, here's the data source and Alice's public key. And now we show that the plain text is the same as delivered, and we'll print it. Now, normally, maybe some of you have seen this demo before, typically the next thing I do is spin up 3 Ursulas on my laptop, and we'd show the demo and be incredible that the NuCypher network is running on my laptop. I remember I was sitting next to Yevgeny at, I think was at ETH Berlin or somewhere, and I was like, oh yeah, I have 3 nodes running on my laptop. And he was like, oh yeah, me too. I don't know if it was ETH Berlin. It was a ways back. But, so yeah, we've just, again, I want to impress upon you that we are in this very excited state, having just transcended from I'm running 3 nodes on my laptop to running an actual testnet where the nodes have, you know, a learning relationship with each other. I don't know if this is going to work, to be perfectly honest. I hope that the logic in this code makes sense to you. I can run it on my laptop. I'm not even going to try to do that. I'm just going to try to run it on our testnet. I really don't know if it's going to work. We'll see. I'll try running it right now. I don't know if I deleted anything syntactically meaningful. Here we go. This is all the log emissions from Alice and Bob learning about all the nodes. Oh, there it is. That's the NuCypher testnet running before your eyes for the first time I've ever showed it to anybody. So that line, just for super clarity here, line 200 retrieved is the same. That's what you're seeing here, retrieved, and then the line from Finnegan's Wake. So yeah, it's been a long adventure, and obviously we're driving toward mainnet. I think I don't know if you got the same impression that I got from the presentation by Livepeer just now, but the impression that I walked away from was like, whoa, people are going to use this. And it's hard to create that feeling in the blockchain world because there, of course, is a lot of fear, uncertainty, and doubt about whether this can ever be used. I think people are going to use this. I think people are going to use Livepeer. I think people are going to use Fluence. And I think it's cool for us to start showing things that people can use. And so that's what I hope that I've done for you just now. I'm going to play a little piece from Final Fantasy IX, and then we will take questions.